So far, regarding the conservation laws, till now we have discussed mainly the three conservation laws. You have studied conservation of lepton number, conservation of baryon number, and the conservation of isospin. You have seen that actually the lepton and baryon numbers remain conserved in all the three interactions, that is electromagnetic interaction, weak interaction, and strong interaction. And at the same time you have seen that isospin remains conserved in only in a strong interaction, while the third component of isospin remains conserved also in weak interaction, electromagnetic interaction, along with the strong interaction. But when the field of study of elementary particle was extended, there were discovered so many elementary particles whose properties were somewhat strange. They actually behave not like just the particle discovered previously. They have some strange properties. In fact, it was seen that the process in which these elementary particles are produced and the reactions involved, the reactions in which these particles were involved, was not found to be consistent with the conservation of baryon and lepton numbers. Although baryon number and lepton number was conserved, even then it was seen that the process does not take place. So you can say that only the baryon and lepton number are not sufficient to deal with the world of elementary particle. And so after the discovery of such strange particles, it was needed to assign a quantum number which was very new for that time. And actually those particles behave in a strange way. For example, you can say that when these particles are produced, it is seen that the particles are produced not singly, it is always produced in pairs. This was a strange property. And in similar manner, when the decay was studied for these particles, it was seen that such particles suffer the decay process not only in a particular way which was allowed for the conservation laws invented till that time, but these particles also suffer some in decay process which was not known at that time. So to clarify the observation, two very famous scientists, first one was M. Gale Mann and another was K. Nishijima. In fact, both of them independently introduced a new quantum number for such strange particles, and that quantum number is called a strange number, and it is denoted by the symbol S. In fact, this strange number, or you can say the strangeness, not a strange number, but this strangeness number is defined for hadrons. It means it is not defined for leptons. So whenever you are encountered with leptons in any reaction, you cannot assign any strangeness quantum number to the leptons. Only hadrons are assigned the quantum number which is called a strangeness quantum number. So first of all, I would like to acquaint you with the values of this strangeness quantum number for the different hadrons, and you have to remember it. In fact, in a tabular form I have mentioned the strangeness number for different hadrons here, and I hope you will remember these values, because when you will remember these values for different hadrons, you will be able to answer all those questions in which these strange particles are involved in any reaction. That when question will be asked that the process is will be possible or not, or the process is allowed or not, you can decide on the basis of the strangeness quantum number. You should remember that actually this strangeness quantum number is also an additive property, just like the lepton number and the baryon number. So whenever a process will be allowed on the basis of this strangeness quantum number, definitely before the process the algebraic sum of the strangeness number of the reactant must be equal to the algebraic sum of the strangeness quantum number of the products. So for that you should remember the values of the strangeness number for different hadrons, and I have mentioned the values of this strangeness quantum number in this table, and you should note that I have actually mentioned here the strangeness number S for different hadrons, and what will be the strangeness number of the antiparticle of a particular hadron. You should remember whatever the value is for a particle, the value for the value of the strangeness number for the antiparticle will be just of opposite sign. So see here, in fact I have mentioned here the class of the particle. The first class of hadron is called mesons, and here I have mentioned the different particles of this class meson. The first one is pion, and you know pion has actually three charge states. This is pi plus, pi 0 and pi minus. And I have also mentioned here the antiparticle of the particle. So for the pion pi plus, the antiparticle is pi minus. Pi 0 is itself its antiparticle. So I have mentioned here self. And the antiparticle of the pi minus meson is pi plus. Okay. And for all these pions, that is pi plus, pi 0 and pi minus, the strangeness number is 0. And you know the sign of minus has no significance before 0. So all the antiparticles of these pions, that is pi minus, pi 0 and pi plus, all these will have the strangeness number 0. Okay. Now the second particle of the class meson is kaon, and actually kaon is also of three types: K plus, K0 and K minus. You can see here. And the antiparticle of K plus you can see is K minus, and that of K0 is K0 bar, and K minus is K plus. And the strangeness number for K plus is plus 1. See here, this is a strangeness number of K plus. So if I will ask you what will be the strangeness number of K minus, which is actually the antiparticle of K plus, as I have told you, I have mentioned here that antiparticle have S, the negative of those shown in this table. So if K plus has the strangeness number plus 1, this antiparticle K minus will have the strangeness number minus 1. Okay. And K0, it has also a strangeness number plus 1. And so its antiparticle K0 bar, it will have actually the strangeness number minus 1. And K minus has a strangeness number minus 1, and so K plus will have a strangeness number plus 1. Okay. Now the third particle of the class meson is eta particle, and it is of two types. This is denoted by the symbol eta 0 and eta prime. And antiparticle of these particles are nothing, they are itself it's antiparticle. So its strangeness number is 0 and the strangeness number of their antiparticle will be also 0. So you have to remember this. Okay. Now the second class of hadron is baryons, and among the baryons the particles are what? First one is called nucleons, and in nucleons you know there are two types of particles, proton and neutron, denoted by the symbol P and N, and their antiparticle will be P bar and N bar. And these nucleons, that is both proton and neutron, have a strangeness number 0, and their antiparticle will also have a strangeness number 0, because you cannot put minus before 0, because minus has no significance before 0. So the nucleons and antinucleons both have a strangeness number 0. Have you learnt it? Definitely you have learned. No. The another particle of the class baryon is lambda particle. Okay, and this is actually a strange particle. Remember this. Lambda particle is denoted by the symbol lambda 0 and its antiparticle is lambda 0 bar. Okay. Now the strangeness number of this lambda 0 is -1. So what will be the strangeness number of lambda 0 bar? Can you say? Definitely you can say this will be +1. As I have told you that if lambda 0 has a strangeness number -1, lambda 0 bar, which is actually the antiparticle of lambda 0, that will have a strangeness number +1. Okay. Now the another important hadron is sigma particle, and this sigma is actually of three types. These are sigma plus, sigma 0 and sigma minus, and their antiparticle is simply denoted by this symbol. Sigma plus antiparticle is sigma minus bar, sigma 0 antiparticle is sigma 0 bar, and sigma minus antiparticle is sigma plus bar. Okay. Now this sigma plus, sigma 0 and sigma minus, all these three sigma particle has a strangeness number -1. Okay. So what will be the strangeness number of their antiparticles? All these three antiparticles of sigma particle will have the strangeness quantum number +1. Okay. Now the another baryon is actually Xi particle, and this is of two types, Xi 0 and Xi minus, and their antiparticle is denoted by the symbol Xi 0 bar and Xi plus bar. Okay. And the strangeness number of Xi 0 and Xi minus, both of these Xi particle has a strangeness number -2. And so the strangeness number of their antiparticle, that is Xi 0 bar and Xi plus bar, both of these will have the strangeness number +2. Okay. Now the last baryon, which is called omega particle, this is omega minus and its antiparticle is omega plus, and omega minus has a strangeness number -3, and so this omega plus will have a strangeness number +3. Okay. Omega plus will have a strangeness number +3. Okay. So I have mentioned here the values of a strangeness number for the different hadrons, and as I have told you, you have to remember this. Okay. And as I have told you that this strangeness number is an additive property. It means whenever you will have to find the total value of a strangeness number in a particular reaction, then you have to add algebraically the strangeness number of the all particles involving in that reaction. Okay, and this strangeness number remains conserved, it remains constant in fact in a strong interaction and electromagnetic interaction. It means it does not remain conserved in weak interaction. So you will see later on that a process which will be allowed by the conservation principle of this strangeness number, uh, which is actually not allowed by the conservation principle of strangeness number, that will be allowed by the weak interaction. You can see, we will see later on. So now I want to clarify the idea of this conservation of strangeness by taking a particular example. You can see that I have shown here a reaction that when pi minus and pi plus get interacted, then we get sigma minus and k plus. Okay. Now you can see that this process is allowed or not allowed on the basis of a strangeness quantum number. You can see. So I have mentioned here the strangeness number of different particles involved in this reaction. You can see pi minus, you have just seen that pi minus has a strangeness number 0 and proton has also a strangeness number 0. So the total strangeness number of the reactant, that is the strangeness number of pi minus plus a strangeness number of proton, that will be what? I have mentioned it here, that this is sigma Si, means the sum of the initial sum of the strangeness number of initial reactants. Okay, so that will be 0 plus 0, that will be simply 0. Now the product is sigma minus and k plus, and you know sigma minus has a strangeness number -1 and k plus has a strangeness number +1. So sum of the strangeness number of the product will be what? I have mentioned it here. This is summation SF. F means final. That will be -1 plus 1, that will be 0. So what you are seeing here? You can see that the total strangeness number before the process was 0 and after the process it is again 0. So you can say that the total strangeness number does not change, that remains conserved. And so if you want to find the value of change in a strangeness number after this process, what will be that? That will be simply 0. So delta S is 0. So this reaction is allowed on the basis of the conservation of a strangeness number. Okay. Now let us consider another example. If we consider that this pi minus and pi p get interacted and the product is sigma plus and k minus, you can see that on the basis of charge conservation this reaction is also allowed, because the charge of the reactant is 0 and charge of the product is also 0. But if you check, this reaction is possible on the basis of conservation of a strangeness number or it is not possible, you can check it. For this, let us write the strangeness number of all the particles involved in this reaction. You know that pi minus has a strangeness number 0 and p has a strangeness number also 0. So the total strangeness number before the reaction, or you can say that the sum of the strangeness number of the reactants, that is simply equal to 0. Now sigma plus, this has a strangeness number -1 and k minus has also a strangeness number -1. So the sum of the strangeness number of the product, that will be simply equal to -1 minus 1, that will be -2. So what you are seeing here, before the process the sum of the strangeness number of the reactants is 0, but after the process the sum of the strangeness number of the product is -2. So you can simply say that the strangeness number does not remain conserved, because before the process it is 0 and after the process it is not 0, it is -2. So there is a change in a strangeness number in this reaction, and so you can say what will be that change? Delta S, this will be -2 minus 0, that is -2, which is not equal to 0. So in this reaction you can say that the strangeness number does not remain conserved. So this process is not allowed via the strong interaction. But you should remember here that this process is allowed through the weak interaction. As I have told you earlier, a process which will be not allowed on the basis of conservation of a strangeness number, that is on the basis of a strong interaction, that may be that may occur through the weak interaction. So this reaction also occurs through the weak interaction. Okay. Now one thing here you should remember that if in a reaction the strangeness is conserved, the reaction has a large cross section. It is found experimentally that as this process is allowed on the basis of strangeness conservation, so this process has, or this reaction has, a large cross section, and this process which I am just showing here is not allowed by the conservation of strangeness. So this process has not a large cross section, it has a small cross section, and it is as I have told you that it is allowed through the weak interaction. So this is all about the strangeness quantum number and its conservation. You have to note here that definitely to solve the problem based on this strangeness conservation, you must remember the value of a strangeness quantum number for all the hadrons, and definitely you should be in your mind that for lepton we do not define a strangeness quantum number, it is defined only for hadrons. And what are the different values of strangeness quantum number for different hadrons, you should remember, and then you can check the conservation of strangeness number is valid, is holding or not in a given reaction. Okay. So in the next lecture we will see the other conservation principle in very detail.